Trying to understand the shape of something is an exercise that we have been doing since our childhood. In everyone's home, there was that toy where you have to put blocks in some holes of the correct shape, the cube in the square hole, the cylinder in the circular one, and so on. But we didn't stop there and continued to study more and more complex shapes, from the star to the spiral, from the house to the the torus. We have experienced so many different and complex shapes that the question, what shape is it, is quite meaningless. Or maybe not. Let's try to define the shape of something bigger and more complex. A whole city? No. A continent? No. The Earth? Neither. The flat Earth? No. The universe? Yes, the universe. Okay, I know that was not a great climax since the title is literally The Shape of Universe. But hey, in my mind it sounded cool. In order to find the shape of the universe, we must face a great problem. When we try to determine the shape of a normal object, we observe it from the outside, but we clearly can't do the same for the whole space. So, we must find another way to get it from the inside. So, how do we find out the shape of the universe? One thing we can do is to investigate how geometry behaves in cosmos. Let's see what it means. With a bit of common sense, we can assert that we can choose any 2 points of our universe and ideally measure the distance between them. In mathematics, something that has this property is called metric space. But let's focus a bit on the concept of distance. Imagine being at the beginning of a straight road that ends with your house. What is the distance between you and your home? It is clearly the length of the street, or better, the length of the vector that has you and your home as ends. And what if you want to walk to a cafe nearby before going home? What is the distance in this case? Actually, it doesn't matter what path you are going to walk. The distance always remains this vector, because it is the shortest possible. This is called triangle inequality, and it is one of the properties that a distance must satisfy. The distance between 2 points is the shortest path possible. In terms of vector, the distance between you and your home is the vector z, whose magnitude is lower than the sum of the magnitude of any other couple of vector x and y. Now, imagine being in a similar situation, but the street in front of you is curved, because between you and your home there is, a work site. In this case, you don't need to consider the straight segment between you and your home, because you can't pass through the work site. The solution is to remember the previous property. The distance is the shortest path possible. So, it must necessarily be the length of the curve that passes near the work site. Remember, the distance is the shortest path possible in accordance with the constraints of the space itself. This generalization of the concept of distance is called geodesic. Now we settle the rules of the game, but how does they help us to find the shape of the universe? Well, for simplicity, let's see their consequences on 2-dimensional figures. First, we took one of the simplest figures, the plane. Imagine taking something flat, for example a paper sheet, drawing 2 different points A and B, and then the distance between them. The line you just drew is clearly a straight segment that starts from A and ends in B. But what if we do the same thing on something that is not flat? Maybe a sphere. If you choose 2 points on that sphere and try to figure out what is the distance between them, you must follow the constraint given by that object. You must stay on the sphere surface. This time, the shortest path between A and B, that is the distance, is a curved line that follows the sphere surface. We just found out that the features of the distance between 2 points is related to the shape of the object on which these points are located. But the same happens in 3 dimensions, and consequently in the universe. If the space is flat, the distance between 2 points is a straight line. Otherwise, if the space is curved, the distance is curved as well. Okay, now we know how we can figure out the curvature of the universe. But this leads to another problem. How do we understand if a line is straight or curved? If we observe a line on an object from the outside, it's easy to see its features. But don't forget that we live inside the universe. In order to study the curvature of those lines, we have to get help from a Greek philosopher and mathematician, Euclid of Alexandria, that laid the foundation of the Euclidean geometry, also called the plane geometry, that is the mathematical system that can be applied to flat objects. The idea is simple. If the Euclidean geometry works in the universe, then the universe itself is flat. Otherwise, the universe is curved. One easy way to investigate if this geometry is the correct one for our universe is to draw a triangle and look at the sum of the internal angles. If we do this in a plane, we always find that the sum of the 3 angles is 180 degrees, no matter what triangle we choose to draw. But if we do the same, for example, on a sphere, we notice that it's different. Let's choose a peculiar triangle in order to realize this difference immediately. Draw the vertices of the triangles, one in the, let me borrow geographical terms, please, North Pole, and 2 on the equator. The distance between these points are curved lines, as we saw previously. But there is something strange. The oblique side of the triangles are drawn on 2 different meridians of this sphere. But that means that they are both perpendicular to the equator and consequently to the base. The sum of the internal angles of the triangle is 90 degrees plus 90 degrees plus the value of the missing angle. In conclusion, the result is surely more than 180 degrees. And this happens with every triangle. If this happens also in the universe, we will say that it has a positive curvature. We stress the word positive because there is another alternative that is a key feature of a hyperboloid-like space. The space will have negative curvature if the sum of the internal angles of any triangle drawn in it is less than 180 degrees. Perfect! Now we only have a couple of things to understand. First, how do we draw a triangle in the universe? Second, what triangle is better to study? The answer of the first question is light, or better, electromagnetic waves. We learned that the distance between 2 points is the shortest path possible, and Albert Einstein teaches us that nothing can be faster than light. That means that if nothing can travel between 2 points faster than light, there isn't any shortcut. The path followed by the light is on a geodesic of the universe. Well, yes, it sounds like we are in a superhero anime or something similar, but we are going to use a triangle made out of light, literally. But which triangle must we choose? If we choose a little one, we don't see the shape of the cosmos, but only the shape of that little piece of space. Furthermore, we also know that locally, in particular near something very massive like the Earth, the universe can be curved. Thanks again, Albert. And our result can be distorted. So, if we want to know its geometry globally, we must choose one of the biggest triangles ever. Astrophysicists chose a triangle that has a vertex here on the Earth and the other vertices at the very borders of the universe, or better, the observable universe, from where we can see a particular radiation, the cosmic microwave background, that is a remnant from an early stage of its evolution. We won't go into details of this kind of electromagnetic wave, but you must know that it is something like a thermal scan of the ancient universe, and those spots of different colors indicate hotter points in red and cooler ones in blue. Knowing the dimensions of those stains that were calculated very accurately, scientists defined a triangle of very precise dimensions that allows to calculate the angle in the terrestrial vertex in the case of flat and curved universe. Measuring that angle is the last step of this journey, and the result may be astonishing for someone. Guess what? The universe is flat, or at least globally. In conclusion, yes, the universe is globally flat, but don't worry, it doesn't mean that it's compressed as a very thin pizza. It only means that it has no curvature, and the Euclidean geometry is the correct mathematical system to describe it.